Hey guys, welcome to lesson 4.3 for science. The first thing we're going to do is go over lesson 4.2. So make sure you have your stuff out for that. I'm sorry that I didn't specify the other day whether or not you needed to do the practices with me, but hopefully you at least followed along so that you're learning that math and what's involved in it. Now from now on, what I told Sadi when she asked me is that if I don't say it, you're not obligated to write it down, but it is good to try to remember to write that down as you take notes from the lesson. But it's hard for you to maybe kind of get into a routine of all the things that we exit here in each of the videos and stuff like that. So if I don't specify, it's not something I'm going to take points off for, just to let you know. Okay, the concept review for 4.2, question number 1 says, what characteristic of a gas is the ability to be squeezed and compacted into smaller containers? The answer is compressibility. Number 2, which law can be stated as follows? If the temperature of a gas remains constant, its volume and pressure are inversely proportional. Remember that when you see that something is constant, that means that's the one thing that's not going to be in the formula. So all you really have to do is go look for the formula that only involves pressure and volume, and that one is going to be Boyle's law. Number 3, how are the volume and temperature of a gas related if pressure is held constant? Okay, so in that case, pressure is the one that's not inside the formula. So the formula is going to be the one that only involves volume and temperature. If you look at page number 91, that is Charles' law, and we know that that's a direct relation. As one goes up, the other one goes down. That's the relationship that they're looking for. Number 4, what is the temperature at which gases theoretically have 0 volume? And that's going to be 0 Kelvin. Okay, 0 Kelvin or negative 273.15 Celsius. That's explained on page 92. Number 5, use the kinetic theory to explain Amundsen's law. Okay, first of all, I'm going to read the paragraph because it's on page 93. It says Amundsen's law under the gas laws and kinetic theory, and then I'll explain it to you in my own words. It says, like Charles' law, Amundsen's law is explained by an increase in temperature causing the molecules to collide with the container more forcefully and more frequently since the volume cannot increase. The increased force increases the pressure on the container. Similarly, the molecules of a cooling gas collide less forcefully and less often because the container cannot contract. The pressure decreases instead. So what's happening, you guys, is that we're talking about fluids, right? Okay, you're talking about a fluid and a gas inside a container that cannot expand, cannot contract. Okay, it is what it is. This container will not change its size, right? So Amundsen's law, if we look at page number 92, is pressure over temperature equals pressure over temperature, which means as the temperature increases, the pressure increases. And at first you're kind of like, well, really? Why? Because as the temperature, let's say that you have water, okay? Well, let's go back to page number, let me see if I can find it really quickly to show you what I'm talking about. Okay, if you go back to page 83 from section 1, remember that we were talking about the 2 fundamental rules that make kinetic theory true. One is that all molecules of matter are in constant motion. The second one is that the warmer an object is, the faster its molecules are going to move, okay? And so then we talk about the fact that the faster that they move, then the faster that the forms of matter, the states of matter, solid, liquid, gas, are going to change because as the temperature increases, they change forms because the molecules are moving faster. So you would assume that there's not as much pressure on top of molecules of gas because they're bouncing off of each other and going in their propio mundo and not coming together, remember, to have that cohesion that they talk about in 4.1. However, when you come over and you're talking about the gas laws inside the container, guess what happens? Inside a confined space, they're going to be colliding off of each other, but they can't go anywhere, right? So if they can't go anywhere and they're in a small space, what's going to happen? The pressure is huge. Think about like a group of 20 children. Where do you want a group of 20 children that have just had sugar? Do you want them in a small room, or do you want them all over the place? You want them all over the place, right? Because you want them to have space to stop hitting each other, etc., etc. Well, that's the same thing with gas molecules. If they're inside a container, a volume that cannot change, if the volume that cannot change, what's going to happen to the pressure? It's going to increase, because all of a sudden there's too much movement inside of here that they don't have room for. So that's how the pressure increases. Okay, so using kinetic theory to explain Amundsen's law, temperature increases. When temperature increases, pressure increases, because the volume cannot increase to give the pressure a break, basically. So the pressure has to increase. Okay, that is Amundsen's law. Number 1 for the application, why must scientists use an absolute temperature scale when applying Charles' law and Amundsen's law? Okay, here's why, you guys. Because if you're using Celsius or you're using Fahrenheit, you're going to have a different ratio of how things increase, because it's a different scale. In that case, you're not going to know, is it double the temperature, triple the temperature, because it's going to depend on what scale you're using. So you have to have a universal scale to decide, so everybody knows at what ratio things are increasing or decreasing, instead of like a fraction for Fahrenheit and double for Celsius. Okay, look at number 2. Many products and sprays, such as hairspray or paint, contain gas under pressure. Their labels contain a warning to keep them away from heat or fire. Why do you think that is? Because Amundsen's law, as temperature increases, pressure increases. So if you already have something that's under pressure, which means that it's at its maximum pressure. If you add more pressure inside this aerosol can, what's going to happen? It's going to explode. Well, if you put heat up to that can, it's going to explode, because you're creating more pressure inside of it and it can't contain it. And something like that's in aluminum, what's the solution? It's going to explode, okay, because it can't contain that much pressure. Okay, number 3 says a gas has a temperature of 125, a pressure of 50, and a volume of 3. The volume increased to 6.5, the temperature is held constant, and then the temperature is reduced to 50 while the pressure is held constant. Use the gas laws to determine the final temperature, pressure, and volume of the gas. Okay, I wanted to have it on the board for you so I can just talk you through it, because it's a little complicated, right? Because really what's going to be happening is the temperature is going to change twice. So change once. So the second temperature you get is its final temperature. The pressure is going to do the same thing. It's going to change once, and you're going to get the second pressure for your final temperature. But the volume is going to change 2 times. It's going to be the original to the second one to the third one, and that's going to be your final temperature. So we're going to need to use 2 separate formulas, right? So let's read through it. It says the volume is increased. So first of all, we have our originals, 125, which you have to change over to Kelvin. So add 273, so it's 398, right? You have your pressure 50 and your volume 3. The volume is increased to 6.5 while the temperature is held constant, which means automatically we know we're going to be using Boyle's law, P1V1 equals P2V2. Because the temperature is held constant, so that we need to find pressure, the second pressure. Even though it doesn't say that, we know that's what we need to do, because automatically we hear that the temperature is held constant. So we find our second pressure is 23.1. Done with that. Then it says the temperature is then reduced to 50. So all you have to do is go 50 plus 273, and that's your final temperature. But we need to use that, because then it says the pressure is held constant. So now you're using this formula, V1 over T1 equals V2 over T2. However, to get your final volume, but you've already switched volumes one time, okay? So you're going to be using V2 to V3 actually. So it's V2 over T1 equals V3 over T2, because volume is already changed from the original, okay? So then you go 6.5 over 398, which is the original temperature, V3 over 323, which is the new temperature, and so you're going to get 5.3 as your volume. Okay, now we can get into 4.3. Go over to page 94. The very first thing you want to do is you want to give me 2 sentences on what is atmospheric pressure in your own words. We talked about air pressure. We talked about water pressure. So what is atmospheric pressure? And basically, you're going to read that paragraph and give me some technical meaning to it. But atmospheric pressure is a pressure that you're feeling right now. There is a ton of pressure on you. Right now, you're basically like in a sea of air, a sea of the atmosphere. And this sea, this mar, is also sitting on you just like the ocean would, okay? But because it's evenly distributed, you don't feel like you're being crushed, okay? But parts of your body will, like your ears, feel different when the pressure changes because the pressure is definitely there, okay? Next, I want you to give me 5 sentences on Torricelli and barometers, the original barometers, the history of barometers, but I want you to do that from the video that I'm about to put in here, okay? Because I think that something like that is something that needs to be shown visually instead of just read. Okay, so I don't need you to take any information from Torricelli's discovery or the barometer, the liquid barometer section. If you don't want to, you can take it strictly from the video and even skip that reading because they're going to give it to you in the video. Okay, but you can also read it if that is your desire. So let's go ahead and do that first, and then I'll tell you about the next tema.
Aristotle famously said, "Nature fears of empty space," when he claimed that a true vacuum, a space devoid of matter, could not exist because the surrounding matter would immediately fill it. Fortunately, he turned out to be wrong. A vacuum is a key component of the barometer, an instrument for measuring air pressure. And because air pressure correlates to temperature, and rapid shifts in it can contribute to hurricanes, tornadoes, and other extreme weather events, a barometer is one of the most essential tools for weather forecasters and scientists alike. How does a barometer work, and how was it invented? Well, it took a while. Because the theory of Aristotle and other ancient philosophers regarding the impossibility of a vacuum seemed to hold true in everyday life, few seriously thought to question it for nearly 2,000 years, until necessity raised the issue. In the early 17th century, Italian miners faced a serious problem when they found that their pumps could not raise water more than 10.3 meters high. Some scientists of the time, including one Galileo Galilei, proposed that sucking air out of the pipe was what made water rise to replace the void, but that its force was limited and could lift no more than 10.3 meters of water. However, the idea of a vacuum existing at all was still considered controversial, and the excitement over Galileo's unorthodox theory led Gasparo Berti to conduct a simple but brilliant experiment to demonstrate that it was possible. A long tube was filled with water and placed standing in a shallow pool with both ends plugged. The bottom end of the tube was then opened and water poured out into the basin until the level of the water remaining in the tube was 10.3 meters. With a gap remaining at the top and no air having entered the tube, Berti had succeeded in directly creating a stable vacuum. But even though the possibility of a vacuum had been demonstrated, not everyone was satisfied with Galileo's idea that this empty void was exerting some mysterious yet finite force on the water. Evangelista Torricelli, Galileo's young pupil and friend, decided to look at the problem from a different angle. Instead of focusing on the empty space inside the tube, he asked himself what else could be influencing the water. Because the only thing in contact with the water was the air surrounding the pool, he believed the pressure from this air could be the only thing preventing the water level in the tube from dropping further. He realized that the experiment was not only a tool to create a vacuum, but operated as a balance between the atmospheric pressure on the water outside the tube and the pressure from the water column inside the tube. The water level in the tube decreases until the two pressures are equal, which just happens to be when the water is at 10.3 meters. This idea was not easily accepted, as Galileo and others had traditionally thought that atmospheric air has no weight and exerts no pressure. Torricelli decided to repeat Berti's experiment with mercury instead of water. Because mercury was denser, it fell farther than the water, and the mercury column stood only about 76 centimeters tall. Not only did this allow Torricelli to make the instrument much more compact, it supported his idea that weight was the deciding factor. A variation on the experiment used two tubes, with one having a large bubble at the top. If Galileo's interpretation had been correct, the bigger vacuum in the second tube should have exerted more suction and lifted the mercury higher, but the level in both tubes was the same. The ultimate support for Torricelli's theory came via Blaise Pascal, who had such a mercury tube taken up a mountain and showed that the mercury level dropped as the atmospheric pressure decreased with altitude. Mercury barometers based on Torricelli's original model remained one of the most common ways to measure atmospheric pressure until 2007, when restrictions on the use of mercury due to its toxicity led to them no longer being produced in Europe. Nevertheless, Torricelli's invention, born of the willingness to question long-accepted dogmas about vacuums and the weight of air, is an outstanding example of how thinking outside of the box, or the tube, can have a heavy impact.
Okay, after the Torricelli, so now you're understanding how much pressure, atmospheric pressure has, on how it's different with water, it's different with mercury, it's different with the different densities of liquids. Unfortunately, we can't use the mercury barometer as much anymore, the same thing with the thermometers. Okay, but so what I want you to do is I want you to also give me 3 sentences on different types of barometers, the aneroid and the altimeter, Okay, and then I want you to give me 3 sentences on the advantages and disadvantages of every kind of barometer mentioned. The mercury barometer, the aneroid barometer, and the altimeter barometer. So 3 sentences on what those two are, and then 3 sentences on the advantages and disadvantages of them. Okay? Then, I just want you to give me 6 sentences on everyday understanding of atmospheric pressure. Everyday understanding of atmospheric pressure, that's going to come from page 97. Page 97. Why? Because you're going to talk about how straws work, pajillas is la palabra, and how breathing works, okay? Basically, the principle between these two, I'll give this to you in my own words, and then you can read it and get your own words for the question. But what happens is look at the very first sentence of page 97. Many devices use the simple rule that fluids tend to move from areas of higher pressure to areas of lower pressure. It is a rule, it is a characteristic of fluids. Fluids can be liquid, fluids can be gases, right? That if they're in a place of high pressure, they're going to find the place of low pressure and flow there automatically. So if you have a straw, if you really pay attention, you're going to see that you don't have to do much work to suck up your liquid into your straw. Why? Because what is happening is when you put the straw into your mouth, there's a lot of pressure being put on the liquid from air, from the atmosphere, okay? So where is the area of high pressure? The area of high pressure is in the fluid, okay? You put your straw in there and you just take one little suck, and what happens? You have reduced the air pressure in the top of that straw that's on the top of the liquid. You have reduced the pressure there, okay, by giving more room, okay? So what happens? The liquid automatically is going to flow to the place of lower pressure. And that's why it's going to do it easily to get into your mouth, because you have reduced the pressure from sucking out that air. Okay, that's how a straw works. It's the same thing with breathing, right? You have muscles up here. Okay, so like think about your lungs almost like a balloon. Okay, what's going to happen if let's say I open my mouth, right? Let's picture my lung as a balloon. And I automatically, when I open my mouth, that means, or when I involuntarily realize I need to breathe, okay, because nerves in your body are doing the thinking for you, your muscles on the top of your lungs are going to go like this. Okay, why? Because what would happen to a balloon if I squeeze it up top? What's going to happen down here? It's going to expand, right? When it expands, what happens? There's less pressure because you have done what? You have increased the volume. So you have increased the volume, which means you have decreased the pressure, according to Boyle's law. So the air in the atmosphere is now going to go where? Straight to your lungs, because it is seeking a place of lower pressure. So your muscles involuntarily expanding the volume of your lung have created lower pressure inside your lung, and the air is going to find it. Now when you're ready to exhale, your muscles are going to contract, just like you would take your hand off the balloon, and the volume would decrease because it would equalize itself all the way through. The volume decreasing would increase the pressure, so now the air needs to find lower pressure, and the lower pressure is now in the atmosphere, and it's going to exhale and push that air back out. Okay, so that is how air pressure affects our breathing and affects the use of things like straws. Pretty cool, huh? Okay, so then after that, you do the concept review. Let me check right now if you can do all of them or if we want to skip a few. Okay, on these, I don't want you to be doing the application. I just want you to be doing the concept review part. Okay, there you go. Have a great day.